It's an honor to be opening this session, the series of matter under pressure. The matter under pressure that I'm going to talk about is related to what is beneath our feet, towards the interior of our planet. So I'm going to tell you a story that started 4.5 billion years ago, when the solar nebula started to condensate. First, it formed small pebbles from the dust of the nebula. Then these pebbles started to form planetesimals, and towards the end of the accretion process, you formed the rocky planets, and among the rocky planets is of course the Earth. At the end of this process, there was a lot of energy that was being accumulated from these high energy impacts, and the planet was very hot, possibly completely molten. And that favored differentiation. So the heavy stuff sank to the center and formed what we know today being the Earth core. The Earth core is very important for our planet for a number of reasons, primarily because this is the place where the magnetic field is generated. Also, you have these convective motions in the liquid part of the core, which is a metallic, is made of a metal, and this generates electric currents, and from this you get to the magnetic field. So how do we know all this? We cannot go much deep inside the Earth. We can't look much more than a few kilometers. So the only way that we have to infer about the properties of inside our planets is to look at seismic waves. So when you have an earthquake somewhere close to the surface, this generates waves that travel not just on the surface, but also inside the planet. And these waves, they follow the path that depends on the properties of the materials they travel into. And in particular, they change directions, so they are refracted when they meet, for example, an interface. So here it's an interface between the mantle and the core. And so by looking at the travel times of these waves on an array of seismographs all around the Earth, we can infer about the properties of the materials inside the Earth, and in particular, we can infer about specific boundaries, such as the core mantle boundary, so the boundary between the mantle and the outer core, and then a boundary between the outer core and the inner core. So these seismic waves have velocities. Typically, you have two kinds of seismic waves, P waves and S waves, or primary and secondary, or if you like, pressure waves and shear waves. Pressure waves have a velocity that depends on the properties of the materials. So here in this equation, you have the density at the bottom, and then you have these two quantities here, K and mu. K is the incompressibility, so it is, if you like, the resistance of the material when you try to compress it, and mu is the shear modulus, so the resistance when you try to shear it. S waves, they only depend on the shear modulus, and so you can see from that equation that they are slower. That's why they're also called secondary waves. They arrive later. Now, in this graph here, you can see the speed plotted as a function of depth, starting from the surface all the way to the center of the Earth. And you can see that the speed increases in both cases until you reach this point here where they both dramatically decrease. And in particular, you see that you lose completely the S waves. So that is what tells us that that part of the Earth is liquid, as it cannot support shear waves. And then as we go deeper, finally, we have the reappearance of these shear waves. Okay? And by the analysis of these seismic waves, then you can construct a plot of density as a function of radius in this case. So in this case, we start from the center of the Earth, and here is the surface. And so the density here, it's 13 grams per cubic centimeters. Then you have a little drop due to the phase transition between the solid and the liquid, and then the big drop, which is due to the fact that you go from a material that is completely different. So the Earth's core is made of something which has roughly twice the densities of the mantle, which is made essentially of rocks. Now, the Earth's core is where the magnetic field is generated, and this is a dynamic generation. So it's not a static dipole moment. It's generated dynamically in changes, not on geological time. We can see, for instance, the direction, the position of the North Pole changes on a yearly basis by quite a large amount, and also the intensity is changing. What is plotted here is the intensity of the dipolar component of the magnetic field over the past 120 years. And you can see that it has dropped quite significantly by something like 7 to 8%. So the magnetic field is decreasing. In 2013, the European Space Agency launched a mission of satellites that started to measure the magnetic field very accurately around the planet. And after 6 months, they produced this image that shows the difference in the magnetic field that was measured in June 2014 minus the field in November 2013 when it was launched. And you can see in blue regions where the magnetic field has decreased, and in red where it is increased. And the scale, this is of the order of a few percent of the intensity of the magnetic field in the Earth. So it's not negligible. You can see there is an overall decrease, which is not negligible on a scale of 6 months. If you look at longer period, so this is 800,000 years, you can see fluctuations of the field are quite common. This is where we are now. Okay? So the field is decreasing, and this is where we are now. We are still higher than the long-term average. You will notice here that 800,000 years ago, the field was very low. That is when there was an inversion between the North Pole and the South Pole, and this inversion is usually accompanied by low field values. What happens when the field is low? Well, the main function of the field today and over the course of the Earth is the one of protecting us from the solar wind, which would otherwise strip the atmosphere of the Earth away. This is what happened to Mars, by the way. Okay? In the past, Mars had the magnetic field and an atmosphere, then it lost the field and it lost the atmosphere as a result. So when you have this low field region, then you have very low protection of the atmosphere. And in fact, it is debated in the literature that these inversions are also correlated with, maybe correlated with mass extinctions due to change in the oxygen content in the atmosphere. We know that the field has been around for most of the age of the Earth. We have data of field stored in rocks that go back at least 3.5 billion years ago. So it's most of the age of the Earth. So this process of convection in the outer core must have been going on for all this time. How can you sustain convection? Well, one way to do it is to use thermal convection, right? In a gravitational field, if you have heat at the bottom, then this heat would cause thermal expansion of the material, which becomes less dense and would rise. But this can only happen if the material doesn't lose heat by conduction too quickly. Okay, so if it escapes because it's a very good conductor, then it doesn't have time to expand, and convection stops, thermal convection stops. So this process is entirely related, entirely driven by the value of the thermal conductivity of the material. Another way of having convection in the Earth is by compositional convection. So what we know is that the Earth's core is mainly made by iron, but it also contains some unknown light impurities. Could be oxygen, perhaps sulfur or silicon. And as it grows mostly pure purely, and so it expels these light impurities, which can deliver the gravitational energy to the convective process. So you see that there are a number of questions that we need to understand if we want to understand the Earth's core, and in particular how this convective mechanism works. So what is the value of the thermal conductivity inside the planet? What is the temperature distribution? What is the actual composition? So it is made of primarily of iron, but what might be the light impurities in the Earth? So these are questions that are mainly material science questions. So you want to know these properties of the materials that make up the Earth's core. So how do we answer this question? Well, of course, we would like to do experiments, directly experiments on these materials, which you can do typically using mainly these two techniques. Okay, so this is a diamond unbuilt cell. You can see two diamonds here. You put a sample here in the middle. Then you apply high pressure. I mean, you apply the forces at the two ends of the diamonds, basically by screwing them together. And this generates high pressure here in the middle. And with this device, you can reach today pressures that are close to those found at the center of the Earth. You can also shine lasers through the diamonds, as they are transparent to light, so you can heat up the materials. Or another way of doing experiments at high pressure is by doing shock waves, creating a shock wave in the sample. So you have a long gun, so this could be 20, 30 meters, and you have a projectile that is launched at high speed in this gun, typically up to 10 kilometers per second, so 10 times the speed of a bullet. And then upon impact, you generate high pressure and high temperatures. And you have to make your measurements during the impact, which is at a time of the order of a few nanoseconds. So with these experiments, you can build what is known as a phase diagram. Okay, so in this graph, what you see here is temperature on this axis and pressure on this other axis. And what is important here is the pressure at the center of the Earth, or in particular, actually not the very center, but the boundary between the Earth's core, the outer core and the inner core, 330 gigapascals. So these are the pressures that we are talking about. And why are we interested in the phase diagram of iron here? Well, the reason is because this is mainly made of iron. So you have a solid here in equilibrium with a liquid, and so the temperature at the boundary is going to be the melting temperature. So if you know the melting temperature of iron at that pressure, then you have a proxy for the temperature of the core. Right, so on this graph you see various lines. Here in the low pressure regions, these lines separate different crystal structures. So here at ambient conditions, you have the alpha phase, so that's the common iron that we find in everyday life. It's a cubic structure. Then when you compress it, it goes to a different crystal structure, the epsilon phase. So this is an hexagonal structure. So it's what you see by stacking oranges at the supermarket. That's that sort of structure. And then as you increase the temperature, eventually you melt the material. So this line here represents a separation between a solid and a liquid. But this line here also represents a solid-liquid interface, such as this one. Why do I have three lines? Obviously, I should have only one line. The reason why I have three lines is because these are three different experiments, so three different groups. So as you increase the pressure and you increase the temperature, so as you reach more extreme conditions, doing experiments becomes more and more difficult, and that's why you have this disagreement between the experiments. And so if you're trying to use these experiments here to infer about the melting temperature of iron here, you can see the quite large range of error that you may have. But what is it that determines the stability of a material? Is it liquid? Is it solid? And if it is solid, which is the structure of the material? Well, there are a number of thermodynamic quantities that are relevant to study, to determine the stability of the materials. One of them is the internal energy, the average internal energy. So that is the energy that is involved in the interactions between the atoms in the materials. The average interactions in a liquid is going to be different from the average interaction in a solid, and different solid structure may also have different average interactions. So that's one component, and the one that has the structure that has the lowest internal energy has an advantage of stability compared to the other. But that's not the only one, because if you are at high temperature, then a very important quantity is the entropy. And you may think of the entropy as related to the number of configurations available to a structure. The more configurations are available, then the more likely the structure is going to be realized. And so the entropy actually enters with these terms, minus Ts. So at high temperature, a structure which has higher entropy is going to be very much favored. Entropy is going to dominate as you go to higher and higher temperatures. But if you compress the structure as well, then you also have an effect caused by pressure, and in particular through a term which is the product of the pressure and the volume. That would be the volume per atom here. So a structure in which the volume is smaller is going to be favored, right? So if you're trying to get on a crowded bus, it's more likely to get on if you are a small child than if you are a big man, right? So these three quantities, they play together. Often they play against each other. And what is actually determine the stability of the material is the sum of these three terms. That is known as the Gibbs free energy. The structure that has the lowest Gibbs free energy, the phase, the lowest Gibbs free energy wins. So this is, let me show you now an example here. So this is a structure of BCC iron. So that's cubic iron, which I'm simulating and showing you a simulation of this structure at 330 gigapascals and low temperature, 500 Kelvin. And you can see that it's gone to somewhere else from where I started from. Right? It's gone to something that is very close to this omega phase, which is a different structure, different crystal structure. And indeed, if I do the same on this structure, the omega phase, simulation at 500 Kelvin, you see that this structure remains stable. So there has been a phase transition from this to this, because the sum of these three terms, so the Gibbs free energy of this structure at that temperature and that pressure, is lower for the omega phase. What happens if I go to higher temperature, much higher temperature now, 6,000 Kelvin, and that's the temperatures that you are expecting at the center of the Earth, close to that temperature. Again, the BCC phase up there, I do the simulation, and you see that, okay, the atoms are moving around much more, but the BCC phase remains stable here, this structure. What if I start from the omega phase and I start to simulate at this temperature? Well, you can see that it goes to this phase here. So yes, you have a phase transition to the BCC phase. Now, in this case, we are quite fortunate that we can see these transitions on the fly, if you like. We can see them in a very short time. That's not always the case. Sometimes there's a big barrier, so you would have to wait for a very, very long time or an impossibly long time in a computer simulation. And so that's not usually the way to proceed to infer about which structure is the most stable. So the way that you typically proceed is to go back to the fundamentals. So thermodynamics, as we said, the structure that wins is the one with the lowest Gibbs free energy. So you calculate the Gibbs free energy, and then you look for the structure which has the lowest one. For example, if you're looking for the melting temperature of the material, then you would calculate the Gibbs free energy for the solid, you would calculate it for the liquid, and then the melting temperature is defined by the point where the two cross. I'm bringing in here the Helmholtz free energy. You can write the Gibbs free energy also as the sum of the Helmholtz free energy plus the PV term, because this is a quantity that we typically like to work with. So this quantity can be calculated with, in a computer effectively by solving, if you like, the second law of motion of Newton, mass times acceleration equal to the gradient of the potential. By solving this equation in time, then you can sample a relevant ensemble, and with that you can calculate these thermodynamic quantities. Quantities like the internal energy, pressure, volume, and temperature are straightforward to evaluate. They are thermal averages. The entropy is not. The entropy is a bit more difficult to calculate, and we shall come back to that in a minute to see how we do that. But obviously, if you want this to be accurate, what is determining this dynamics? It is the potential energy here. This is the quantity that determines how the atoms are going to move. And so you need to use a potential energy that is realistic if you want to obtain a realistic free energy. Now, the interactions between the atoms, what determines how the atoms moves, are the electrons, and the electrons are quantum particles. They have to be described using quantum mechanics. And we are close to 100 years now. It's 99 years from the development of the Schrödinger equation, which, as we know, it describes how quantum particles interact between themselves exactly. The trouble with the Schrödinger equation is that it can only be solved analytically for very simple systems, the systems with a low number of electrons. And when I say low, I really mean one. Okay, so you already with 2 electrons, it is impossible to have an analytic solution. And it's not just that, but it's also very difficult to approximate it. So to study materials by solving directly the Schrödinger equation is not going to go very far, particularly if you want to study high temperature properties. So the field really got a boost in the mid-60s when Walter Kohn, who was on sabbatical in Paris in 1964, with his postdoc Peter Hohenberg, developed this new theory that he called density functional theory, in which the relevant quantity was not the wave function anymore, but the electronic density. The theory is exact, is formally exact, is just a reformulation of quantum mechanics. The only trouble is that the solution of the theory has to be found for a new Hamiltonian that contains terms that are unknown. So in particular, you have this. Okay, so you go from this one Schrödinger equation that gives you as a solution a many-body wave function to n one-body-like Schrödinger equations, which we know how to solve. But now these equations have an Hamiltonian which is unknown. In particular, it contains a term here that is known as the exchange and correlation function that contains all the, if you like, the quantum behavior of the electrons that we cannot describe, that of the exchange and correlation. In fact, it was Feynman, I think, was heard saying that this was called he heard him calling this quantity the stupidity function. But it's a good place where to place all your ignorance, because you can start to try approximate this quantity. And indeed, with this postdoc, when he was back in San Diego a year later, he developed this Kohn-Sham theory, and he proposed a very simple approximation for this function that should have not worked, but in fact it worked extremely well, much better than anyone expected, really. And that is really the success of this theory in material science. Now, today, these functions are continually developed, and probably we have more than 100 of these functions today. So now let me come back to the evaluation of the entropy. As I said, the entropy cannot be calculated as thermal average, so you need a little modification of what you do to calculate it. And what we do it is by using this method that is known as thermodynamic integration. So the idea very quickly is the following. this is the system that you want. Okay, so the system described by your quantum mechanic functional, so density functional theory functional now. So this potential U. And what you do is you introduce a different system, a reference system, which is much easier to treat and for which you know the free energy. It doesn't have to be necessarily very close to you, this reference potential, though it helps if it is in terms of efficiency. And then what happens is that you build a potential that is a mixture between the two. So this lambda is a coupling parameter between 0 and 1, and is mixing the two potentials. Then you do your simulation in which you slowly change this parameter between 0 and 1. So you see these atoms are changing sign. They are a mixture between these two. So you start from this and you change it to this. And if you do this change sufficiently slowly, then the free energy difference between these two systems is given by this integral. So this integral in the lambda of now the thermal averages. Now this is a thermal average of these two potential energy differences. So now you can use, you can evaluate this thermal average over your simulations, and you get this free energy difference. If you know how to calculate the free energy of these systems, and you typically know how to do it, if this is simple enough, then you can get the free energy of your system. Okay, so now we've got all the ingredients, and we can start using them to test if the theory works to describe properties at high pressure. So here, what I'm plotting is the pressure against volume curve on the eugonio. So this is the typical relation, pressure-volume relation that you have in these experiments here that I mentioned earlier. And you see here the calculations that are these lines compared to the experiments that are these squares. And here on the right, you have the speed of sound in the material, again as a function of pressure. And you can change the pressure by changing the speed of the projectile, by the way. And again, you can see the comparison between the calculations and the experiments. So this DFT, this density functional theory, for these properties of iron at high pressure works extremely well. So then you can apply this to calculate the free energies of the solid and the liquid, and from that you can get the melting curve, which is this black line here. And this is a work that was done 25 years ago now, and later on new experiments were performed, and they started to produce new data, and this new data they all agreed with the previous calculation. So this is one of them, this green dotted line. So what is the temperature of the core then? Well, the temperature of iron, the melting temperature of iron is 6,300 at this pressure, but the core, as I mentioned earlier, is not made of pure iron, and so we need to take that into account because the presence of impurities may change the temperature. Such as, seawater has a different freezing temperature than the water that we drink. So we know that the core is not pure iron because of what comes on the Earth as meteorites. So these are iron meteorites with sulfur inclusions here. But we also know that because the properties of pure iron, so this is speed of sound as a function of density, that they are not quite matching that of the core. So we know that there are some light impurities in the core, and these light impurities are also responsible for a density jump at the inner core boundary that is not the same of what you would have if the core was pure iron. So one thing that you can do is to try to develop a strategy to constrain the composition of the core by using what we know experimentally from seismic data and what we can calculate. So the hard datum from seismology is that the density change here at this boundary is of the order of 5%. If that was, if the core was pure iron, this density change would be much lower, less than 2%. So that means that there is some partition of light elements at this boundary. So you can start to introduce hypotheses and test them. And for instance, the most simple hypothesis that you can do is that the core is made of a binary mixture. So iron plus one light impurity. So iron, the solvent A, plus one light impurity, the solute X. Equilibrium here at the boundary, again, with the laws of thermodynamics, requires that the chemical potential of, is effectively Gibbs free energy per atom, if you like, of the light impurity has to be the same between the two regions. And these chemical potentials depend on the concentration. So the equality, this equality in general will result in having two different concentrations in the two phases. Now, if you rewrite this chemical potential in this way, so you take out the configurational part, which diverges in the limit of a small concentration, then you are writing it as the sum of this term here, the configurational part, plus an excess chemical potential part, this mu tilde. And then by using these two equations together, you get an expression for the ratio of concentration of the impurity between the solid and the liquid, which is given by this quantity here. So it's related to the difference of these two excess chemical potential differences between the solid and the liquid. And these are quantities that we can calculate, again, with a technique that is similar to the one I described before, thermodynamic integration. We call it alchemy, because in this case, what we are doing is we are choosing one atom of iron in this case, and we are slowly turning that atom into oxygen. By doing that, by looking at the difference of the free energy, you get the difference of the two chemical potentials, and if you know the chemical potential of iron, you can extract the chemical potential of oxygen. Okay, so what are the results for this? Well, we tested three different impurities, oxygen, sulfur, and silicon. And what is plotted here is the density of the liquid as a function of concentration. So if you have zero concentration, that is the density of pure iron, and this is the density of the core. Okay, so pure iron is much too dense. Then you start adding impurity, and the density drops, and depending on which impurity you are adding, you are matching the density of the core at different concentrations. Okay, so given now the chemical potential that you calculate, you can look at the mole fraction in the solid as a function of the mole fraction in the liquid. And let's see what happens in the three cases. Well, for sulfur and silicon, you see you put this impurity in the liquid, and almost the same amount goes into the solid. So there is very little partitioning of this impurity between the two. And as a result, the density jump does not change very much. And in fact, you cannot reach what is the density jump that we measure for the Earth's core. So that tells you that a simple binary mixture of iron and sulfur or iron and silicon has to be excluded based on this data. Oxygen has completely different behavior. You see that you put oxygen in the liquid and then nothing goes into the solid. So the mole fraction in the solid stays effectively almost zero. And so that means that you can increase the density jump very effectively with oxygen, but actually too effectively. So by the time you have enough oxygen to match the density of the liquid, then the density jump is far too high. So even this binary mixture here is not viable. So the hard constraint that you get from these results is that it cannot be a binary mixture. Indeed, if these are the elements, there may be other elements. But based on these elements, none of these satisfies what we know from seismology. But if you put them together, then you can have a ternary or a quaternary mixture in which about 10% of sulfur or silicon is in the liquid with a similar amount of oxygen, and then about 8% in the solid of sulfur or silicon, and almost nothing in the solid. So with this data here, you could match the densities in the Earth. Now, this change in concentration, so there is more light impurity in the liquid than in the solid, is also responsible to a change of melting temperature, in this case in the region of 700 to 900 Kelvin. So this partitioning is what is determining this change in melting temperature, which is effectively what happens, the reason why seawater freezes at the lower temperature than water that doesn't have any salt in it. And that's the reason why we spray salts on roads, to lower the melting point of the ice. Now, this oxygen that does not go into the solid, you see then as the solid inner core grows, it grows with no oxygen in it, so it is expelling oxygen into the liquid. And this expulsion is giving us this compositional convection. So it helps to sustain convection. That's very useful. However, the inner core, we think, is only about 1 billion years old. So how was this convection being sustained before this process started? So before then, before the inner core started to grow, this mechanism was not available. So the general wisdom was that this was due to thermal convection. But thermal convection is, as we said, is entirely determined by the thermal conductivity, which is this constant here that relates the heat flux through a material to the temperature gradient. And it has to be low enough if you want to be able to sustain thermal convection. So up until about 12 years ago, the value of the thermal conductivity in the Earth's core was assumed, and the assumption was based on extrapolation going from ambient conditions, effectively. And it turned out that people were using very low values, and with these low values, thermal convection was indeed sustainable. So the situation changed quite a lot, as I said, about 12 years ago, when a number of people had the tools to start calculating this conductivity. And what I'm putting here are these horrible formulas that I don't want you to read in any form or shape, but I just want to point out the quantity, the most important quantity here, which is the expectation values of the electron momentum. That is basically the physical quantity that determines how well a material conducts heat. If it is a metal, in fact, you've got two components. You have an electronic component and an ionic component, and typically is the ionic component the electronic component the one you are interested in, as the ionic component is only probably a few percent of the total. So if you start applying this theory, you test it. So the first test that was done here was for liquid sodium at ambient conditions, just higher temperatures. And you can see here the calculations here. These are called PB. This is the name of the functional that was used in that case, and compared to the experiments. What you see in this table is both the electrical conductivity and the thermal conductivity. And you can see that the agreement is respectable. If you look at iron, again, in the low pressure region where you have data, so you can test the theory against the experiments, again, the agreement is good. What is plotted here is the resistivity, and it is plotted as a function of the number of atoms in your simulation cell. This is a technical parameter, technical issue. Basically, you need to make sure that your simulation contains a large enough number of atoms, otherwise the results are biased if the simulation cell is too small. So you see here that the result converge when the number of atoms is big enough, and they agree quite well in the experimental range, which is determined by these dashed lines. So once you've done these tests, then you bring these calculations to the conditions related to the Earth's cores, and these are the results. So here you have the temperature, pressure. So these are the likely conditions in the core. So this red range, these are the likely conditions of temperature, pressure inside the Earth. And these are the values of the thermal conductivity. This is the outer core, and this is the inner core. Compared to the data that was used before. So there's a factor of at least 3 increase in the thermal conductivity, which is a very large difference. It makes thermal convection very difficult to sustain. I should mention that the experimental situation is still not clear. There are different groups that predict very different values. So this group here predicts a very high thermal conductivity, even higher than these ones, while these ones predict very low thermal conductivity. And even on the theoretical side, the issue is still open. So these data are based on density functional theory, which does not include explicitly electronic correlations, electron-electron interactions. These are recent data in which this conductivity has been reanalyzed using a more accurate method based on a method that is known as dynamical Mille field theory. It's a paper that appeared just a month ago. And you can see here that there is a difference. So there is a little drop compared to the value of DFT, but you still have very large values. So this is over 100. And the values that people were using to get thermal convection sustainable were in the region of 30 or 40, so very much lower. Yeah. So that is the consequence of this, that the higher conductivity, that the power of the geodynamo is greatly reduced, and that the top of the core may be thermally stratified. So you have all this the heat that is convecting away, but the mantle acts like a blanket onto the core. So it's not accepting all this heat, and therefore the very top of the core starts to try to become isothermal, if you like. So you get this thermal stratification, and the result would be the thermal convection may not be sustainable. But then if you shut down thermal convection, how are you going to sustain convection before the inner core started, so before 1 billion years ago? Well, you could think of higher secular cooling. So secular cooling is the cooling of the Earth from the beginning. And so you could start with the Earth a lot hotter originally, which is possible. However, as I said, the mantle must take all this heat. And it's not clear that the mantle can take all this heat. Well, I'll come back to this in a minute. Another proposal that was put forward a few years ago, initially by O'Rourke and Stevenson, then also by Kei Hirose with different materials a year later, is the idea that originally when the Earth was very hot, then it could dissolve light impurities such as magnesium, magnesium oxide, for instance, in large quantities. And then as the temperature dropped, the solubility dropped, and so this magnesium oxide started to exsolve, so to drop out of the solution. Then, since it is light, it would rise, go towards the mantle, and it would leave a dense iron layer that would sink to the bottom. And this would drive convection. And it's an idea that people are looking at the moment. We are also looking at how to describe this mechanism in more details. But I want to finish with just one last point, which is an idea due to Bruce Buffett in University of California, Berkeley. And his idea is that the Earth's core is in contact with the mantle. In the mantle, there's a lot of oxygen. It's basically an oxide, the mantle. And so is it possible that the core is undersaturated in oxygen? So it's in contact with the mantle, and so it is possible the oxygen may be flowing into the core from the mantle. And why is that relevant? You will see this in a second. So you can look at this. So you can calculate, again, the chemical potential of iron oxide, for instance. So if you imagine that oxygen may travel between the two as iron oxide, so you can calculate this in the mantle and then in the core. And again, equilibrium is given by the point where these two quantities are equal. So you apply your alchemy techniques, and what you find is that, in fact, the chemical potential of iron oxide in the mantle is significantly higher. 1 electron volt is a high energy on this scale in the mantle compared to the core. So this is driven iron oxide from the mantle to the core. And so this may be forming a layer, an iron oxide layer at the top of the core, just below the mantle. And in fact, this layer may also explain some anomaly in the seismic data that show a slow layer at the top of the core. Why is this relevant for the convection story? Well, the reason is because when you have a chemical reaction, then there is also a quantity known as the heat of reaction. So there's you have a reaction, so these reactions may be endothermic or exothermic. So it may result in heat being absorbed or released. In this particular case, the reaction is endothermic. So there is a large heat being taken away from the system. So you move an iron oxide from the mantle to the core, and you take away oxygen. And this is quite useful because it's a heat sink. And so this heat sink may help getting rid of the heat coming from the core because of high thermal conductivity, and so it may help thermal convection again. Okay, so with this I'm finishing. I don't want to spend much time on this. I just want to, I hope I've shown a case in which shows that computer simulation are an effective tool to study matter at extreme conditions. And of course, you can extend these techniques also to different conditions. It is complementary to experiments, so it's mature to a point in which these simulation methods are complementary to experiments and can reach conditions where doing experiments is still difficult. I just want to finish by thanking all my collaborators. Monica Pozzo, she was responsible for most of the thermal conductivity calculations at UCL with DFT. Leonid Purovsky and Yerny Imravlie in Paris and Ljubljana, respectively, they were responsible for the dynamic in-field calculations. And then Fred Wilson, a young postdoc at the University of Leeds, young and talented postdoc of Chris Davis, who is a theoretical geophysicist and is our geophysicist of reference. And then David Price and Mike Gillan at UCL and David Gubbins at Leeds were involved in most of the results that I've presented. And in particular, I'm indebted to Mike for his involvement over the years. These three are all now retired and emeritus professors in these universities. And with this, I finish, and I thank you very much for your attention.
You mentioned
hit the button.
Oh, sorry.
Joe, just hit the button to the front.
Oh. Was that
Silicon.
meteorite?
Silicon.
The silicon, excuse me. What happened to the other elements? Was that just because of what you found in meteorites, or how did you choose them?
Yeah, that's a very, very good question. In principle, any light elements could be in the core, but there are arguments based on cosmochemical abundances, volatility, which make you prefer these three elements. But people are also looking at carbon, hydrogen are thought to be possible elements.
So you mentioned light elements, but you didn't mention heavy elements like uranium, and especially the heat generation due to uranium. Is it something that we know to some extent? Because I expect if you have a lot of uranium in the core, you will have a lot of heat generation in the core itself that may change the results.
It is possible, though the elements that are present in the core, even the heavy one, have to be siderophile, if you like. They have to be iron-loving, right? So to get it to enter into the core. And I'm not sure how much siderophile uranium is. So typically it's not one of the elements that is thought to be in the core. Most of it is probably in the mantle.
Yeah. Thank you for the interesting talk. I had two questions. One is this amount of the seismic data sufficient to be confident about exactly the shape? I'm using an analogy with CT scan. That's my first question. My second question is on the thermal integration. It's almost like perturbation theory. What happens if your reference results in you pick a reference that's in a different phase?
Yes, both very, very good questions. Well, in terms of the data, the seismic data, my understanding, I'm not seismology, but my understanding is that the density inside the Earth is known to within 1%. But this is what I've been told. In terms of thermodynamic integration, yes, you are very right. You have to make sure that in the transition, you don't have phase transitions. Because otherwise there is a discontinuity and things don't work anymore.
I see. So if I may follow up on that, so that's becomes sounds like a chicken and egg. Like you're trying to map out the phase transition. I mean, same problem in condensed matter, universality classes. But is there any indication or any supplemental data?
Well, you may see a discontinuity in as you move from when you change lambda from 0 to 1. You may see in the data that you have something that looks like a discontinuity. So you will typically see. But the way you do it, in theory, you can start from wherever you want, whatever reference system you like. But in practice, you tune your reference system to your final system to be as close as possible.
Right.
So that the transition is, you end up with a smooth transition.
Thank you.
You mentioned that Mars had a magnetic field and that it lost it. First of all, how do we know these two things? Yeah. And third, can that happen to the Earth?
Okay, we know that it had a magnetic field because we can look in the rocks, paleomagnetism. So we can measure that the rocks are magnetized. And we know that it doesn't have one now because we measure it with orbiters. So why did it lose it? Why did it lose it? Yes, because there was convection that stopped, that failed. Convection failed at some point. We don't know how and why. And yes, it could happen to the Earth. I mean, it hasn't happened for 3.5 billion years at least, but it may happen. For instance, when the whole inner core, when the whole core is frozen, then that for sure you will lose the magnetic field.
So the data of the magnetic field over in long years, do you have some other data about the temperature of the Earth or some other variables that?
No, the temperature of the Earth, we have no data. There's no way we can measure it. So the only way to infer is to use a proxy. And the proxy in this case was the phase diagram of iron. The melting temperature of iron. If you know what it is at the inner core boundary, then you can use that as a constraint of the temperature of the Earth. But it's not going to fluctuate. It's going to drop continuously from the beginning of time, the beginning of the Earth, to to now. Yeah, you won't see fluctuation. There's no reason why it should fluctuate. It's just cooling, slowly cooling the Earth.
Yeah, thank you. The excellent talk. I was trying to understand you mentioned that the heat sink of the iron oxide reaction sort of allows you to make convection. Is that, I was trying, or to recreate a convective layer when it wouldn't have existed before. I was trying to understand exactly how that works. Is it just that you get like effectively condensing material that sort of you're cooling at the top layer acts as like sort of the opposite of a heating from the bottom, in that you sort of convect.
You may look at it like that, but the main problem when you have this heat escaping, a lot of heat escaping, and the mantle acting as a blanket, is that this heat has no way to go, so it stays at the top, and you start making the system more and more thermal. You lose the thermal gradient that you need for convection, right? But if you can get rid of this heat, either because the mantle let it escape it, or because you have this reaction, this endothermic reaction, then you don't have this heat accumulation.
Okay.
Question about the thermodynamic integration. You mentioned the melting curve of iron when you were calculating it for the liquid phase. How did you choose the reference state for, say, the liquid iron?
Okay, the reference for liquid iron. Yep. We experimented it a little bit initially, but we ended up realizing that a simple inverse power potential was describing the energetics of the system very well. And so the reference system in that case is simply 1 over R to the alpha, where alpha is close to 6. This system here describes iron very, very closely.
I see. And the system is also liquid at the same condition?
Yes.
Oh, I see. Yeah. Thank you.
Thank you. Is the connection between a planet losing its magnetic field and losing its atmosphere simply that the solar wind will blast the atmosphere away without a magnetic field to protect it? Then how is it that the Earth did not have its atmosphere blasted away during previous epochs when its magnetic field was much weaker, in between changes in direction? We are closer to the sun than Mars is, and the solar wind is more powerful here than it is out there.
It's a fair point. It's a question of how long you stay without magnetic field and how long do you have to stay before you lose the atmosphere. Okay. And indeed, if you look in the literature, as I mentioned very quickly, these inversions are linked in some papers to mass extinctions because of change of oxygen content in the atmosphere. So they may have been long enough to change the amount of oxygen, but not long enough for us losing all the atmosphere. We should also remember that the atmosphere is continuously replenished on our planet by volcanic eruptions.
Okay.
That also helps to hold the atmosphere. But if the Earth were to lose the magnetic field, it will lose the atmosphere.
Just maybe I missed something, but from the point of view of geologists, for instance, the lower mantle is very reduced to the point that it has solid iron in it. So it's very difficult for me to imagine how you sequester oxygen from lower mantle that is in equilibrium with iron, with metallic iron, into the core. So I would see the metallic iron sinking into the core, but not the oxygen. This is in regards to one of the last points in your lecture.
Yeah, no, I see your point. This is what comes out from the calculations. The chemical potential shows that it is more stable in iron at this high pressure and temperature,
right?
Than in the
mantle. It's just interesting, yeah. Thank you.
going with questions, but we're going to give the speaker a break after this fascinating talk. So please join me in thanking.